Okay, so first of all, thank you for waking up early and coming to this lecture. So, as Dario said, today I'll be talking about topological insulators and topological superconductivity, mostly focused on the system I've been using, which is Mercury Telluride. And most of the work that I'll be referring to has been done in Würzburg while I was a postdoc, but you may wonder why I'm affiliated to Paris now. It's just I recently moved to Paris. So this work mostly has been done in collaboration between Würzburg and Tokyo, and I want to acknowledge right now all the people who have done an amazing work, apparently, especially my PhD student at that time, Jonas Wiedenmann, and we've had great help from Teun Klapwijk as well. Okay, so in this lecture I'd like to do two things. First, I would like to give an overview of what Mercury Telluride is and why we can use it to realize not only one topological phase but many. And in that respect, it will be focused on Mercury Telluride, of course, but this will be a complement to what you've seen yesterday with Leslie and Claudia, in the sense that Leslie and Claudia always look for new material and use new techniques to grow new crystals and so on. In our case, we have one material from the start, and we will use different techniques to fine-tune the system and try to go to different topological phases. And this has advantages, but also drawbacks, and I'll try to tell you a little bit more about that. And this should take about, I don't know, half an hour maybe. And then I would like to move to the core of this lecture, which will be topological superconductivity. So I don't want to do very complicated things. I think you can find that in many papers nowadays. I'd like to do very basic things. First, because it's Friday morning and you're all tired. Second, because I'm no good at complicated things. And also because I want everyone at the end of the lecture to understand the very basics so that afterwards you can go to more complex papers to learn the details, but to put everyone on the same page and understand what the Josephson Junction is, how it works, and so on. So let's start with first normal transport in Mercury Telluride. So as you may have heard yesterday already, Mercury Telluride is a 2,6 semiconductor where you find the mercury here and the telluride here, and it's usually grown in heterostructures together with cat telluride, which uses cadmium, which is here. These semiconductors have zinc blende structure, which means that it's two FCC that are with tetrahedral coordination, which means that you have two FCC that are translated by half or a quarter of the diagonal here. But what is important for us, so these zinc blende structures are very well known. Gallium arsenide is also in that case, and so on. And there's a very conventional way of seeing the band structure of these things. But what makes the difference with Mercury Telluride is twofold. First, mercury is a very heavy element. And you may just say, okay, it's only one line further down than cadmium, but it actually has all this line in between. So there's a huge difference in the mass between the cadmium and the mercury. And this will make a huge difference when you look at relativistic correction. And on top of it, you also have, because all of these are in the right position in the periodic table, they also have strong spin-orbit coupling. So in combination, the combination of the two effects will lead to strong changes in the band structure if you compare with something like gallium arsenide, and this will the reason why this Mercury Telluride is a topological insulator. Then another thing I want to point out already right now is the fact that Mercury Telluride and the cadmium telluride that we use to grow the heterostructure have very similar lattice constants. And you may think, oh, they're almost the same, this is going to be perfect. You're going to grow cadmium telluride and Mercury Telluride one layer after the other, and everything is going to give you a perfect crystal because the lattice constant is almost the same. But actually, this difference of 0.3% is already enough to induce strain in the crystal, and this is one of the ingredients that is used in Würzburg to constantly go from one topological phase to the other by just tuning the strain. And I'll try to show you how we can actually play with the strain to go from one topological phase to the other. Okay, so the basic of the band structure, I guess you've seen before, and this has been also showed yesterday. In conventional semiconductors, usually of that type, you have that type of band structure where you have an S-type band here at the top as a conduction band, and you have a P-type band here as a valence band. But Mercury Telluride, because of these very strong relativistic correction, has an inverted band structure here, so that the P-type band lies above, and the S-type band lies below. And because of this, you will naturally have band crossings at the interface between these two materials, and this is where the topological states come. Now, one thing that you see here is that Mercury Telluride is in fact a semi-metal. So the Fermi energy lies in between the two subbands here. And this will be very annoying for us because it would be a topological conductor, which is not very interesting. If you don't do it carefully. So we'll have to find ways to lift the degeneracy here and open a small gap. So the way we do that is twofold. First, you can either use quantum confinement to open a gap. So you confine in the z direction, and you create very narrow quantum wells like this. And in that case, this quantum confinement will be enough to open gap in the bulk. And this is how you go to a two-dimensional regime and to a two-dimensional insulator. So you always have these topological states that run around the boundary, but the bulk becomes insulating due to this quantum confinement. The second thing you can do is use strain. Strain reduces symmetry, and it lifts the degeneracy, especially at the point where the two subbands touch each other. And this is how you can grow thicker layers, because strain it restrains you a little bit in terms of the thickness of the layer you can grow, but you can actually go to a 3D regime where there's real 3D transport. And in that case, you go to a three-dimensional topological insulator where you have surface states circulating all around and a real insulating bulk. And I'll show you actually that you can also play with a strain to go towards a Weil or Dirac semi-metal phase. Okay, so first a few side remarks on all of this. In most cases, I will refer to the other material as cadmium telluride, but in real life, we mostly use this type of compound, which is mercury cadmium telluride, but it's also a conventional semiconductor, so I will use both interchangeably without noticing, and the physics is the same, so you should not bother, it only changes a little bit the numbers. Again, one thing I told you is the fact that the mass of the mercury atom plays a huge role. And you may sometimes hear that spin orbit is responsible for these topological phases arising. But in mercury telluride, if you look at how the bands look like at the beginning for cadmium telluride and mercury telluride, and how they change as you add the different relativistic corrections, well, you see that the Darwin correction basically does not too much. The mass velocity correction is not too strong for cad telluride, but it is huge for mercury telluride because mercury is that heavy. And then the spin orbit coupling shuffles around the bands again and splits them, but the biggest correction is actually the mass velocity correction. And finally, just a side remark, I'm not sure you know that, but the appearance of these surface states is known since the 70s from works by Volkoff and Pankartov. But they had not realized, of course, the topological origin of these states. And, well, basically, if you read their papers, they always say that, yes, there are surface states, but they don't care so much about that. Okay, so let's go to first let's try to learn more a bit about these quantum wells. So I told you that to realize the quantum well, what you do is you create a thin quantum well of a few nanometers, and you use quantum confinement to open a gap. So what happens is that if you create this quantum well between the mercury telluride and mercury cadmium telluride or cadmium telluride, you will have two-dimensional states that will lie in the potential well between the gamma 6 and the gamma 8 bands. And what matters is whether the electronic band or the hole band are actually in the correct order. So if you grow it too thin, if the mercury telluride is too thin, then the band inversion that takes place in the mercury telluride does not take place in this very narrow quantum well. Just you may think that somehow the cadmium telluride or the mercury cadmium telluride is way too thick in comparison with the mercury telluride, so that the band structure of the mercury telluride adapts too much to that of the cad telluride. And the band inversion does not take place, so the electron band lies still above the hole band, which would not be the case for bulk mercury telluride where you see this decline. So in that case, you have no band inversion and the quantum well is trivial. Now if you grow thicker quantum wells, then of course at some point you will get the band inversion, and this will be reflected in the fact that the hole state here lies above the electron state here in the quantum well, and this gives rise to the quantum phase transition, and this is where the quantum spinel effect appears. And typically you can calculate this bench, yeah? That's similar to that. Actually, you can calculate the full band structure, and you see it here. So what's happening here is that in very thin quantum wells, you have these 2D states here and these 2D states here, which are these two states. And as you enlarge the thickness of the quantum well, then you see that at some point the two bands will touch here and there, and then they will go into an inverted regime, where a gap opens up again, but this time it's a topological gap, so you have edge states that will appear here in between. Well, you also see that the band structure has this funny camelback structure, which is sometimes very annoying because this means that the valence band is very, very flat, so it has very, very high effective mass, which means lower mobility and so on, which can be annoying in transport, but I will not refer to that too much in the talk. Okay, so how do we grow these quantum wells? Well, you've heard Leslie yesterday talking about crystal growth in different methods. The one we use in Würzburg is the one that she doesn't want to use because it's extremely slow and she wants to grow thick, very, very big crystals. In our case, we like to use this method because it's very, very accurate. You can grow things very slowly, which means you can grow them with a very good precision on the thickness and so on, and this is how you can realize very good quantum wells. And this is not a new technique. This has been used for I don't know how many years in gallium arsenide technologies and so on. But this is responsible for the very high quality of the crystals and their very good mobility. They have very low defect density also, which means that they have very low doping, and which means that naturally the bulk is insulating. You're very close to the gap. You're not deep in the valence band or deep in the conduction band, as you may have heard from the bismuth compounds, which means that you're very close to the gap and you have a very good insulating bulk. Now, one thing about this thing is, as Leslie said, it's super slow, which means that we will not grow a full crystal. We basically grow only the top layer, which is maybe something like a few hundreds of nanometers, and it takes a few hours to do that. So you would never grow crystals that are millimeters in thickness. And the way to grow this crystal, of course, you will not grow very, very, very thin crystal. They would break very easily. So what you do is that you start from a commercial substrate, which has been grown by the techniques Leslie presented yesterday, which are good in quality, but not as good as the quantum wells we want. So we first grow a buffer to try to somehow smooth the roughness at the surface of the substrate. And once the buffer is thick enough and the roughness has been smoothed out, then you can grow the structure here that you see. And the structure may look complicated, but it's in fact a mercury telluride quantum well here in yellow, and then some barriers at the top and at the bottom. And the barriers here include some doping in iodine to be able to dope the Mercury Telluride quantum well, but this is accessory. The problem with Mercury Telluride is that since I told you the gap at the beginning does not exist, Mercury Telluride in itself is a semi-metal, the small gap you will open either from quantum confinement or from strain is always very small. Small means in that case 20 to 25 millieVs. And if you remember, gallium arsenide has a gap of about 1 electron volt, so this is much smaller. But also some compounds like the bismuth families also have much, much larger inverted gap of the order of hundreds of millieVs. So we're very far from that, which means that we need to be very careful when tuning the gate voltage and so on. Tuning the density in the gap is rather difficult and will easily connect to the valence band and to to the conduction band. So this is, the good thing is high mobility, the bad thing is very small gap, to summarize. So you may have seen many results on these quantum wells in the past. These were the first to be studied as topological insulators, at 2D topological insulators. And I heard at the beginning of the week that there was a discussion about whether this conductance quantization could be reproduced at all, and whether this was maybe just an artifact or a matter of luck. This is indeed, I'm not going to hide it, this is indeed very hard to get good quantization in these quantum wells. Nevertheless, recently the lithography has been massively improved and keeps the crystal quality in also very small structure, such that recently we've been able to see quantization that now look much better than the ones from the past. It's not a log scale anymore, it's a linear scale, and it's more or less reaching the plateau. So this is a good sample. Not all of them are like this. Sometimes they are a bit here, sometimes they are a bit there. We're still trying to fine-tune those structures and understand what limits the quality of this structure. And this gives me the opportunity to somehow point to the open questions that we have as experimentalists in this field. The main question we have right now is, how can we improve the robustness of these edge states? How can we make these edge states really usable for anyone, so that we could send crystals all around the world and people could start to do quantum spinol physics and real quantum spinol physics, and not material science that would be dedicated to only improving the quality of this crystal. And there's lots of work that have been done in this direction, and that show that even if these quantum spinol edge states are supposed to be protected against backscattering, actually there are many mechanisms that can lead to backscattering. They always implicitly break time reversal symmetries or things like this. I'm not going to enter details. But one particular example is disorder. It's since you have a very small gap, it's very hard to tune the Fermi energy homogeneously between the conduction band and the valence band, meaning that as soon as you have potential fluctuations, you will have charge puddles appearing, which would be huge islands of charges coming from the valence band or the conduction band, and if they get too close to the edge states, then it's not clear how this will affect the transport here. And there are proposals that explain that it leads to backscattering and so on and so forth. So that's one of the directions we try to follow and try to understand. Now another thing we can do with these quantum wells is fine-tune the band structure. And one way to do that is to add a magnetic doping. And in that case, the magnetic doping is made with manganese atoms, which are isoelectric but paramagnetic. And in that case, what you can do is, since they are paramagnetic, you can use these magnetic dopants to induce something like an internal magnetic field. As soon as you switch on a small magnetic field, they will have their paramagnetic response and will enhance this. Pictorially, they will enhance this response and lead to very large spin splittings. And this helps you to enter the quantum anomalous Hall effect, which you have heard earlier this week, which means that somehow, because of this fake magnetic field that you create with this doping, you will somehow stabilize. You will start from this situation and you will stabilize one edge state but destabilize the other one. And progressively, if you switch on this spin splitting far enough, then you will go to the quantum anomalous Hall effect, which has only one edge state circulating in one direction. And there's a formula for the spin polarization which comes from standard paramagnetism. Here, these manganese atoms have 5½ spins, and this is very dependent on temperature and magnetic field, but if you do that, then you can reach a quantum Hall plateau at very, very low magnetic field. So here you see we have nu equals -1 for very, very low magnetic field of the order of something like 70 milliteslas. I think this is very exciting because this opens the way to very robust edge states, the ones from the standard quantum Hall effect, basically, except that you get them for very, very low magnetic field, and then you can combine them with superconductors, which usually don't like magnetic fields. And this is maybe one way to go towards Majorana states, which relies not on the quantum spin Hall edge states, which are very fragile, but something like the quantum Hall effect, which is much more robust. And if you want to know more, you can go to that reference. Okay, now let's go to the 3D layers. So now let's forget completely the quantum wells for now. We want to grow thicker layers and go to a 3D regime where you would have the surface states wrapping around an insulating bulk. But as I told you, the Telluride is a semiconductor, but Mercury Telluride is a semi-metal with a Fermi energy lying here. So what you're going to do is strain this Mercury Telluride to open a small gap because the strain lowers the symmetry and lifts this degeneracy. And I'll show you later how we strain this material, but typically the gap we obtain is on the order of 20 milli-EVs. I will show you in detail how we can do that with precision, but the basic idea is the fact that you grow Mercury Telluride on cadmium telluride, and they have very small lattice mismatch between the lattice constants, but this is already enough. The Mercury Telluride will have to adapt to the lattice constants of the Telluride, and because of that, it will have different crystallographic structure and will have slightly different band structure. And that's the way we can do that. And the mismatch is very small, meaning that the strain you obtain is quite small, but this is already enough to open a gap. And in any case, if the strain was too big, what would happen is simply that at some point the Mercury Telluride could not adapt to the cadmium telluride structure anymore, and it would create defects to relax the strain. And if you want to keep a good crystallographic structure in the Mercury Telluride, you have to grow it on something that has very small lattice mismatch and on thickness that are not too big to conserve a good crystalline structure. And this is exactly what has been done. And if you do that, I'm gonna go a bit faster now, but if you do that, you see, you can see, you can do that type of thick Mercury Telluride layers, and you can see that it has a 2D response coming from the surface states because you see quantum Hall effect, and this quantum Hall effect follows the dispersion of Dirac cones, namely 2 Dirac cones, so that you only have the odd integers. Here you have 3, 1, 5, and so on, so you're missing all the even quantum Hall plateaus. Of course, this is only true if the top and the bottom surface have exactly the same density. If you're slightly off in density, then you start to recover some of the plateaus in between. But if you change the density with the top gate, you can actually scan all these different regimes and show that you can somehow extract from, you can classify these plateaus between 2 families, and they would correspond to ideally the top surface and the bottom surface. And you can identify them because the top surface reacts very heavily to the top gate, while the bottom surface reacts less strongly to the top gate. And the same way, the bottom surface has better crystalline quality because it's buried nicely in the crystal, while the top surface is at the top and is more easily attacked by the chemicals during processing, which means that it has lower mobility, and you see all of this. Now for me, the open questions to go further in this direction is how do we do, how do we understand these 3D states apart from their magnetic response? If you go to the quantum Hall effect, of course you've identified the direct structures, but you've completely lost the surface state somehow. You're back to the standard quantum Hall effect. Of course it looks a bit funny because you have top and bottom surfaces, but it's not a three-dimensional topological anymore. So for me, this is very important now to understand how these top and bottom surfaces can talk to each other and exchange charge, either between the top and bottom surface, but also between the surfaces and the bulk. And there's lots of work right now in Würzburg to try to understand how this works, whether when you apply a top gate, how do the charges move, how does the surface states can screen the bulk, and maybe you only move charges on the surfaces but not in the bulk, and so on and so forth. Another way to play with the band structure is again to use strain. So here I told you about the tensile strain, meaning that you push here from the top, and this extends the lattice constant in this direction. Now if you do it the other way around, with a substrate that has a lower lattice mismatch, then you do the opposite. This will push the atoms inwards and will stretch the lattice constant in the opposite direction. And if you do so, you can actually show that naturally you do not push the bands away from each other, but you push them into each other. And if you do so, this means that you will create Dirac points here in the band structure. And you can calculate this, and this will look like this. And this is how you create something like a Dirac or a Weil phase. Okay? And you can do that with DFT calculations. And again, you see something here. So the color scale means how far they are to the surface. The red here means that they are at the surface. So you see the surface states here. They still exist because the overall band inversion between the gamma 6 and the gamma 8 band is still present. But now you've done something to the band structure so that they don't connect to each other anymore. And you've created something here in the bulk, which is given by this white color here. And if you zoom in, you actually see that indeed you've created some Dirac points here and there. And you see that these surface states actually connect to these Dirac points. But one thing I want to emphasize here is that the energy scales are even lower. Here, this is the typical scale I was giving previously, something like tens of milli-EVs. Here, if you want to see these Weil points, you really have to tune within 1 milli-EV. And this appears to be pretty difficult. Nevertheless, if you see that, you see large negative magnetoresistance, which is usually associated with this Weil response. You can tune the magnetic field from vertical to in plane, and you see that you go from a standard positive magnetoresistance to a negative one. You can turn the magnetic field within the plane, and you see that the amplitude of this negative magnetoresistance varies. And all of this follows the prediction for Dirac or Weil phase. This you see only very close to the charge neutrality point, because as I told you, as soon as you gate away from that, you recover something that is extremely similar to a standard topological insulator with standard quantum Hall response and so on. And this is explained, at least understood, by the fact that as soon as you gate away from this Dirac point, if you look at this picture here, then you're back into these standard surface states. So there's maybe a way to get this Weil physics here in these systems, but at the cost of very low energy scales. So this is something that is going on right now. Okay, so I've told you all the kinds of things we can do with Mercury Telluride just by playing with a strain to adjust the band structure. Now I would like to explain how we actually tune this strain. And the way we do that is actually very, very simple. in theory, in principle. In practice, it takes some adjustment in the MB chamber, but the idea is very simple. You start from materials which have different lattice mismatch with the mercury telluride. So this is bare mercury telluride, this is bulk cadmium telluride, and this is bulk zinc telluride. And what you will do is that you will grow what is called super lattices. So you will grow something which is one layer of cadmium zinc telluride, which is in between these two lattice constants. Then you will grow a certain thickness of cadmium telluride, and again, cadmium zinc telluride, and so on and so forth. And by doing so, you will create some strain within the super lattice, and you can adjust the strain by changing. So you always grow only one layer of cadmium zinc telluride, but you grow a given number of cadmium telluride layers. And by doing so, the strain will propagate from this cadmium zinc telluride all the way to the top, but in a different way depending on how much cadmium telluride you've put in between. And there's a formula. If you do the balance of the force, you can find the effective lattice parameter, which is that of the cadmium telluride modulated by this factor here, which depends. What's important here is the thickness ratio. So these guys here. There are mechanical parameters such as stiffness and so on. But what's important is here that you can modulate this ratio. And if you do that, you can actually show that in principle it should follow this line here, which enables you to go from a strain of 1.4% to minus 0.3%. Minus 0.3% is what you need to go into the 3DTI regime. But here you go towards this Weil or Dirac semi-metal phase. And you can actually check that if you do these super lattices, they are actually exactly as predicted. You can do X-ray diffraction to know how your substrate look like and characterize with Bragg diffraction how the lattice constant is. And you basically see that here there's a substrate peak as usual, but here you have interference fringes, and these fringes come from the fact that you have a super lattice. And you can actually check that the distance between these fringes actually matches with the presence with the thickness between these two planes, and that you actually get the correct effective lattice parameter. So you see that with the MBE growth, you get extremely good quality. So somehow, if I want to summarize this part so far, you see that with this mercury telluride platform, you can do extremely good crystal with very high mobilities. And one thing I've not emphasized is the fact that since they have low defect and low doping densities, then the bulk is quite insulating. You can also go from one phase to the other. You can have them coexisting sometimes. And one thing I've not mentioned is that you can also grow nanowires. So this is all very interesting. Now, whether we are ready for topological quantum computing, as you may hear from Delft or Copenhagen, I'm not so sure yet. We have reproducible results, and we like the MBE because it gives large layers which are easily scalable. But there's still a lot to understand about the complexity of these structures and how these phases are actually topologically protected or not. Okay, so this somehow concludes the part, the introduction I wanted to give you on mercury telluride. This was intentionally somehow quite vague and quite as an overview, just to give you some ideas of the structure of the methods we can use to realize this crystal and tune them in a fine manner. So again, this is quite different from what you've seen yesterday. Here we fine-tune the energy scale, while Leslie and Claudia can go to very different systems. It's not so much what we do, but you could understand that maybe in the future we combine both. They find a good material, and with this type of structure, maybe they fine-tune it. And now I would like to go towards the core of this lecture, which is superconductivity. So in that second part, I'll try to be way more precise in what I say. And I will try not to go too fast and do some derivations on the blackboard so that you can follow, but please don't hesitate to stop me at some point. So first, let me try to tell you why we like to study topological superconductivity. And in 2 words, the reason is that here you have on one side, in the topological phase, you have funny electrons which have this helical Dirac dispersion, meaning that they are linear, they have a linear dispersion, but also that they have a spin attached to it. And this spin is very important because in a superconductor, what you try to do is you form Cooper pairs, and these Cooper pairs in the standard BCS picture are coupled with k up minus k down. And if you try to form a Cooper pair with k up minus k down, here, since you only have one value of the spin for each value of k, you see that somehow you don't have many solutions. There's only one type of electron you can do. You cannot do the one that would be k up minus k down or k down minus k up. There's a limited choice. You've lost some degree of freedom in there, and this leads to a special superconductivity. And this is called helical pairing sometimes, or p-type correlations. And I'll try to tell you how this manifests in the Josephson Junction. But this is what's so special about the superconductivity in this system. There are different things you can do with that. Play with the bound states in the Josephson junctions to realize Majoranas, and I'll try to give you in 2 lines why from this system you can build Majoranas. And you can also try to play with spin-orbit coupling in these systems to create some funny Josephson junctions, but this I will not cover today. Okay, so how do you make Majoranas out of this system? Well, I told you try to start from helical fermions. You create a Cooper pair out of that, and because you have only one spin species per k, then you have this funny symmetry. And how do you make Majoranas out of that? Well, you remember that Majorana is a particle that it's its own antiparticle. And the best way to do that is to start from a superposition of electron and holes with equal weights. How do you get that? If you remember your BCS theory, the BCS excitations in a standard superconductor are superposition of electron and holes. But usually they come with a U factor and a V factor here, which are not equal. And on top of that, they come with a spin here, indices, which are opposite usually. But here, you've removed this spin degeneracy, so you only have one spin species per type of particle, so this enables you to very simply forget about this spin degree of freedom. And because of this, this also allows for the fact that there's one state that can appear that is a bit special, that is the one that comes with equal weights. And in a standard S-wave superconductor, this is forbidden because of zero-point motion, but since you have now a P-wave structure, you can have this state at zero energy, which has equal weights on the electron and the hole part. So this is in 2 words how this P-wave superconductivity in principle allows you to create Majoranas. This also tells you how you should look for them. First, you need a topological phase, and you need a superconductor. So this is why people have been looking in the past, but still up to now also, at structures where they combine the superconductor in proximity with a topological phase. So here this is taken from the Delft experiment where the topological phase is created in a nanowire. And they try to look at what's happening at the interface between these two. And for this, they probe the transport in that type of structure where you go from superconductor to topological insulator to a topological phase to a normal metal via, expectedly, a Majorana fermion. But the thing I would like, okay, one thing that we've had in the past is that at some point this seemed pretty hopeless. The signatures were very, very shallow in that case, and people started to talk to us about sayonara fermions. So we hope this is not that hopeless, and we hope that we'll see something about that. But the direction we'd like to follow is a bit different here. People have tried to identify these Majoranas from SN type of structures. In our case, we want to bring 2 superconductors next to each other, and then a Majorana will appear on either side. And if you bring them close enough, the thing that you do is you create a Josephson junction. But this Josephson junction is a bit special because it has this Majorana states at either side. And these Majorana states will couple and will create some very special state in the junction that we would try to identify. And I will try to show you how such a topological junction works and how we can try to identify it. Okay, so this is where I go on the blackboard. And I would like to start introducing you to Josephson junction physics. So first, how many of you know how a Josephson junction works and how to... So that's quite a bit already. That's good. So I will go fast then, and I will would like to point out a few important points on that type of system. So if you remember rightly, so a Josephson junction from the start is something where you bring two superconductors close to each other and you connect them via something. This something can be in principle of any type, normal metal, an insulator, ferromagnet, or topological phase. The initial derivation that I would like to remind you of is the one from Josephson in the 60s, if I'm not mistaken, and was derived initially for an insulating state. And in that case, what you can expect is that the wave function, the macroscopic wave function that describes each superconductor will leak into the insulator and will at some point couple. So how do we do that in practice? Well, the simplest way to do that is to start from a very simple Hamiltonian, probably the simplest you'll see this week, which is the one you see in basic quantum mechanics, where you have two states at stationary states at energy E1 and E2 that you start to couple with a coupling constant K. And if you do that, well, you can derive you have the Schrödinger equations that govern these two condensates. And now I'm going to make the conventional ansatz for the wave function. That for the wave function that describes the two superconductors is of that type, okay? Where Ni is the density of the Cooper pair in the condensate. And if you start from your Josephson equation like this, you can move to equations that will actually give you two equations, one on theta and one on n. And this will give you, in the end, two equations. This is a complex equation, so you will get two real relations. And the one thing you can do is first derive the one that governs the density by just doing this. Okay, and then you combine the two, and you will end up with something that. So I'm not going to redo the whole calculation here. I just want to sketch the derivation briefly, and you will end up with something like this. Okay? And this tells you how the number of Cooper pairs changes in one of the superconductors. And if you want the current, well, the current is carried by Cooper pairs, so you have a charge 2e times n1 like this, n1 dot. And if you do that, well, immediately you see that from the previous equation you have something like that. which is usually written this way. And that's the first Josephson equation, which tells you for a given phase difference between the two superconductors, a current will flow, a supercurrent will flow, which is given by IC sine phi. Okay? So that's the first equation you can get. Now you can try to work on the other, to work again on the equation to get something about the theta. Oh, actually, I messed up the theta here. It's phi. Okay. And if you do that, you just can calculate this. I'll just try to give you the easiest way to go to the solution if you want to do it at home. And if you do that at some point, you can go to something like this. Where I've made the assumption that N1 is approximately N2, okay? Which is not a huge approximation because usually you use the same superconductors for S1 and S2. So this is again with this guy here, phi. You can write it this way, d phi dt equals E2 minus E1 over H bar. What is E2 minus E1 is the energy difference, and that's typically from electrochemical potential equality. This will be equal to 2E times V, where V is the voltage. Okay? And this is the second Josephson equation that you will need. Okay? So from there on, from this very simple model, you see that you can derive two equations that govern the physics of this type of structure. And I would like now to think a little bit about the consequences. So first, you see that one thing you can do is that let's assume the phase is constant, but non-zero. If the phase is constant, then there is zero voltage, okay? But the phase can be constant but finite such that there's still a finite current that flows. And this is the supercurrent. This means that you have a finite current that flows for zero voltage. So typically, from this means that in the IV curve, you'll have something like this. You'll have a first branch that is here. And you can do that, you can find a solution to that as long as the current is smaller than IC, which is called the critical current for obvious reasons. So you will have something like this. Okay? Now, once you start to pass a current that is higher than IC, this means that the phase cannot be constant anymore. And if the phase is not constant anymore, then there's a finite voltage that appears. And typically, this will give rise to something in this region. And believe me, for very high currents, then for very high voltages and very high currents, you recover something that is pretty much linear because you're back to having a lot of voltages and a lot of quasi-particles flowing, so you're back into an ohmic regime. What happens here for now, I will leave it a bit open. It depends on your exact system and so on. But typically, that's the thing I want you to remember. Okay? So we'll elaborate a little bit on this. Depending on the system, again, the overall description can be a bit different. But here, this is the ohmic regime. where you have mostly normal transport, because the supercurrent is only a tiny fraction of the total current. And here, this is the supercurrent branch. Okay, so this was the easy bit. Now, you see that somehow, in the derivation, you can see that this bit here, the critical current here, encodes a lot of information, and especially it encodes here the coupling. While this guy here, this equation does not depend on anything. It's just 2 times E times V. And this has somehow a profound origin, which is the fact that this is all linked to the phase of the wave function, which you basically cannot do too many things about it. It has to follow this E times T over H bar. So this will lead very simply to this relation, while this one depends massively on how you couple the two systems. And what I want to point out here is somehow that the fact that whatever you do, you cannot change this equation. So all the information about the system will be encoded in this relation. And in the Josephson derivation, we've ended up with this very simple formula here. But in practice, and this will be the case for a topological system as well, the formula here between the current and the phase can be very, very different. First, there can be sine phi, but also other harmonics like sine 2 phi, sine 3 phi, and so on, sine phi over 2, things like this. But also, this IC is not always a constant. You can have voltage-dependent current phase relations. You can have dependence on the magnetic field, and so on and so forth. But what I want to point out is that everything is in the current phase relation, or in how the phase will change the current. And that's what I would like in the rest of the lecture to tell you a bit more about, and in particular how this current phase relation looks like when you have a topological insulator in there, and how you can try to distinguish between a conventional system and a topological insulator. Yeah, that's why I'm... Okay. So let's do one more thing. Somehow now, I've described an insulating system. But in a normal system or in a conducting system, the coupling can be described a bit differently, and especially because you have free electrons that can move in the normal part. And in that case, the correct description for such small devices comes from Andreev reflections and Andreev bound states. So we've heard very briefly about Andreev reflections in the previous lectures, so I would like to tell you a bit more about this. So if you assume that you have an electron here that impinges on the interface with a superconductor, then the superconductor has a gap, it's here, and the condensate of Cooper pairs at 0 energy. So you cannot create single particle excitation within the gap. So if this electron comes with small energies, then there's no way it can penetrate as a single electron. So what happens in that case is that you can have Andreev reflection, meaning that you create a Cooper pair in the condensate, which can flow then, and to preserve all kinds of conservation relations, then you have to create a hole on the other side. So what are these conditions, and how can you go further afterwards? So first, you need to have some kind of energy and momentum conservation, which means that if you create an electron, if you have an electron impinging at an energy delta E above this level here, then this means that the hole has to exit with an energy which is EF minus delta E. If you want to conserve the momentum K, then it means that you will have the same kind of relation. So here this is a bit particular. You see that somehow if you have delta K, which is very small, you have Kf, which is turned into, actually it should be minus K, so that this means that the hole will bounce, will be retro-reflected. It's not a specular reflection. At the interface like this here, you have the hole that comes like, the electron that arrives like this. It creates a Cooper pair that goes in this direction, and the hole is reflected here. So this goes in, this is quite peculiar. This is not a specular reflection, but I'm sure most of you have seen these drawings before. Now another thing that you have to remember is that this is a phase coherent quantum process, meaning that you have to match wave functions and so on and so forth. And because of this, there's a phase shift of the wave function at the interface, which is given by this relation here. And I'm not going to derive it. This would take way too long. But somehow you see that there's this phase shift here that depends on the phase of this superconductor here and the energy with respect to the gap here. And this will become very important when we calculate the Andreev bound states. And the last thing you want to remember is that if you send up electron, you have to create Cooper pairs that have spin up and spin down, which means that the hole must be the absence of a spin down electron, so it must have spin up. Okay? So the spin conservation gives you that type of conservation on the spin. Now, what happens if you place two of these interfaces? And this, because this describes an SN junction. If you, okay, a few more remarks. Here I talked about Andreev reflections, because this is what happens if you have a superconductor, but if you have also some dirt or some imperfect interface here, the electron can also scatter normally. It can also be reflected as on any potential step, okay? And we'll come back to that later. So you can have both Andreev reflection and normal reflection in a standard system. Except that you see somehow that here you have to abide with these rules here, so that in the quantum spinol edge states, you cannot satisfy all of these equations because of the helicity. And this means that in principle, in a quantum spinol edge state, you can only have Andreev reflections. So you should have perfect Andreev reflections in these systems, because the normal reflection is not possible. Finally, here I talked about standard retro reflection Andreev reflections, but in Dirac materials, when you have energies that are Fermi energies that are much smaller than a gap, you can have holes that are reflected below the Dirac point for electrons that come above the Dirac point. And this changes a little bit these conservation rules and leads to, in that case, to specular reflections. And these are the specular reflections you may have heard of from the graphene community. So this is something I'll completely ignore, even though we have a Dirac system. This only occurs for a very low doping, and I will just consider that we don't see that. It's been, there are experimental papers that claim they have seen that in graphene. I should have added the reference here, but I will just consider that even though we have a Dirac system, I will ignore that. Is it okay now? See if I stop now? Yeah. Okay. Then later in the second lecture, we'll put two of these interfaces together, and then we'll have a Josephson Junction, and we'll combine these Andreev reflection rules to try to see how Andreev bound states form and how they are different for a standard normal system and a topological system. Thank you for your attention.
Thank you.